If you want to prepare for the freezing, airless vacuum of outer space, you don't go up, you go down. Just off the coast of Florida, sitting 20 meters below the surface, is the Aquarius Reef Base. It is the world's only underwater research laboratory. Every year, NASA sends a dedicated team of astronauts down to this habitat for weeks at a time. Down here, they are known as aquanauts, operating in complete isolation to simulate the psychological and physical realities of an extraterrestrial mission. And the physical realities of the deep ocean are brutal. For every 10 meters you descend, the weight of the water above you increases the pressure by 1 full atmosphere. You might remember the Titan submersible. When it imploded at 3.5 kilometers deep, the vessel was crushed so instantly that the human brain wouldn't have even had the 25 milliseconds required to register pain. Yet, despite this freezing, crushing darkness, NASA is pushing even deeper into the abyss. They study this lethal environment because it mirrors the exact conditions we expect to find on habitable worlds beyond our own. We have this deeply ingrained assumption that all biology relies on the sun. We think organisms need daylight to survive. But the truth is, living things don't require sunlight. They simply require a raw energy source. To find that alternative energy, you have to travel down into the Hadal Zone. This is the absolute bottom of the ocean floor, plunging up to 11 kilometers deep, where tectonic activity creates constant underwater volcanic eruptions. These cracks in the crust form hydrothermal vents. They operate like massive underwater hot springs, spewing thick plumes of mineral-rich water at temperatures reaching 400 degrees Celsius, directly into the pitch-black water. This heat provides the specific energy needed to drive complex chemical reactions. It takes basic elements like carbon, hydrogen, and sulfur and forces them to interact and bond into complex molecules. This specific geothermal reaction in the deep ocean is exactly how the very first primitive biological cells formed on Earth billions of years ago. To find alien life, we don't necessarily need a warm, sunlit surface. We just need to find another dark, geothermally active ocean. That realization points our sensors away from the inner planets and directly toward the massive gas giant of our outer solar system, Jupiter, and the moons trapped in its orbit. The most promising of these is Jupiter's 4th largest moon, Europa. Beneath this frozen shell of scarred ice, Europa hides a global liquid saltwater ocean containing twice as much water as all of Earth's oceans combined. It prevents freezing through tidal flexing. Jupiter's gravity physically pulls and squeezes Europa's structure as it orbits. This constant friction superheats the rocky core, radiating heat upward, meaning Europa's seafloor likely contains hydrothermal vents like our planet. Europa possesses the same parallel blueprint for life that early Earth did. It is a probable biological incubator, sitting right in our cosmic backyard. But reaching that incubator presents a massive engineering challenge. Europa is hundreds of millions of miles away. Traveling there in a straight line is mathematically impossible. We simply cannot carry enough fuel for the trip. To solve this, NASA engineers built the Europa Clipper, a specialized spacecraft designed to navigate the solar system through orbital mechanics rather than raw fuel. Instead of flying straight to Jupiter, the Clipper launches toward Mars to steal orbital momentum. It then slingshots all the way back around Earth to gain the velocity needed to cross the asteroid belt and brave Jupiter's radiation winds. This cosmic pinball maneuver requires flawless mathematical precision, but it is the only viable method we have to deliver our instruments to Europa's doorstep. Once the Clipper finally arrives, it can't just park in orbit. To survive the intense radiation around Jupiter, the spacecraft will perform dozens of intricate, looping flybys past Jupiter's moons, dipping in and out of the danger zone. With every pass, its primary objective is to scan Europa's surface. The Clipper will map the thickness of the ice shell, searching the cracks and ridges for the most vulnerable entry points. Finding those thin spots sets up the next stage of this decades-long project. Future missions will drop nuclear-powered cryobots designed to use their intense heat to melt straight down through up to 20 kilometers of solid ice. The moment these cryobots break through into the liquid water below, they will immediately deploy swarms of microsubmarines. These autonomous drones will swim through the pitch-black ocean to hunt for biological signatures at the hydrothermal vents. We are moving past the era of simply taking pictures of dead rocks from orbit. We are preparing to actively swim through alien oceans. Of course, we have to acknowledge the primary uncertainty. Even with perfect conditions, alien biology might operate on chemical rules entirely outside our Earth-based understanding. There is a high probability of finding absolutely nothing. But right now, the world's brightest scientists and engineers are collaborating across borders, dedicating their careers to chase even a small chance of finding life. Whether we find a thriving ecosystem or a silent abyss, the effort to solve these engineering puzzles moves our entire civilization forward. Each mission to a world like Europa expands the boundaries of what our species can achieve.